log of the natural log of A minus the natural log of A. Now, isn't there another way to write this?
Natural log of A
divided by.
Yeah, so we can write it this way. So natural log of A over. Okay, so does that look good? Yeah. Okay, so let's plug in what we talked about with half-life and see if we can derive a half-life for a first-order reaction. Okay, so if T1 half, or at T1 half, we know that A at T1 half is equal to 1 half A naught. So plug this into this equation and tell me what you get. Okay, so I'll write it over here. So we have the natural log of A. Okay, so we have the natural log of A. This is our half-life. And we have A naught. So we can, look what we substitute in here.
A naught over 2.
George?
1 half A naught.
Okay, so let's plug in the natural log of 1 half A naught over A naught. That's equal to K minus K times T1 half. So note that the A naughts cancel out. So now we have the natural log of 1 half is equal to minus K times T to the 1 half. And if we simplify this equation, what do we get? So we should get T1 half is equal to the natural log of 1 half divided by minus K, or the natural log of 1 half numerically is equal to minus 0.69, or T1 half is equal to 0.69 divided by K. Okay, so this is an equation that we can use for a first order reaction. Okay, so again, the half-life is equal to 0.69 divided by the rate constant K. And again, this is only for a first order reaction. Okay, so you don't want to use this equation for a second order reaction or a 0th order reaction. This is first order only.
So it's 0.69 over K
over
or
K.
Negative K.
Okay, because the natural log of 1 half is minus 0.69, so. Now, let me say that usually method 1 is used rather than method 2 because it's not easy to determine the concentration accurately at each point in a reaction. So for example, you can take a sample out here, but then you have to stop the reaction. So what's one way to get a reaction to stop?
Lower temperature.
Yeah, you have to lower it. You have to lower the temperature a lot, and you want to quench it. Like put it in, freeze your reaction so the atoms will stop moving around. And that's not easy to do. Okay, so usually the easier way to do a reaction rate experiment is to use method 1 rather than method 2. So method 2 sounds good because you only have to do one experiment, but like I said, you have to figure out how to measure these concentrations at different points in the reaction. Okay. Let's see. Let's review this. So let's just say we have this reaction, A plus B going to C. The rate law tells you the order of the reaction, the rate constant, and whether the reaction is exothermic. So what do you think? A, B, or C? Might be more than one answer.
A and B. Answer? Oh, A.
Okay, yeah, so think about this for a minute. Share your answer with the person sitting next to you. See if you guys agree with each other's answer. Okay, so for question 1, does the rate law tell you the order of the reaction?
Yes.
Yeah. Does the rate law tell you the rate constant?
Yeah.
So note that this is what we've written down here. So this is our, in this reaction, A going to products, here's our rate law. Rate is equal to the rate constant K times A to the first power. This represents the order. K is the rate constant. Does the rate law tell you whether the reaction is exothermic? So who says C is correct? Okay, so you're right. So it doesn't tell you. Reaction rate doesn't tell you whether the reaction is exothermic or endothermic. Let's go on to the next question. Zeroth order in B means that if B doubles, the rate doesn't change. The rate doubles, the rate triples. Okay, so who says it's A? Who says it's B? Who says it's C? Yeah, so you're right. So note that if the rate law, sorry, if the order with respect to B is 0, if B doubles, then the rate doesn't change. Let's go to the next one. So the rate constant K changes with concentration, time, or temperature. So here's our rate constant K in our rate law. So is the rate constant going to change with concentration? Will it change with time, or will it change with temperature? Time.
What would it change?
Okay, so who says that the rate constant K changes with concentration? Who says it changes with time? Who says it changes with temperature? Okay, so why don't you discuss this with the person next to you? See if we can come with this. Okay, now there's three terms that we use which involves the word rate. So we have the rate law, and the rate constant. Okay, so there's three terms. So what does the rate constant represent? Okay, so if we go back to this equation here, know that the rate is equal to the change in concentration of A with respect to T. And if we go to this graph here, how can we represent rate on this concentration versus time graph? That would be the the slope. So for example, if we were to draw the slope of the tangent here, that represents the rate at this point in the reaction. If we draw a slope here, this represents the rate at this point in the reaction. Are the slopes changing or are they the same? The slope, that means, is the rate changing or is the rate the same? Yes, note that as the reaction proceeds, the rate changes. Does the rate go faster or slower? Yeah, the rate goes slower. Okay. So note that we just looked at time, so the rate constant K is this quantity here. Okay, so the rate changes with time. Does the rate constant K change with time? Okay, now let me go back to let's go back to this quiz question. Let's see. It's right here. Okay, so in the second part of this question is calculate the rate constant K.